Hello. So I'll talk today about limiting laws in free probability and classical probability too. I mean, it can be quite complicated. And yeah, so we've seen last time that we have at the end of the lecture, we've seen that we have pre-central limiting theorem, and now we'll get into versions of that. So more details, of course, and versions like complex version, also Poisson limit theorem, compound Poisson limit theorem, both classical and free. So try to understand these bijections somehow between classical and free probability coming from limiting theorems, which are pretty much similar. So let's find this this presentation. We are classical and free limiting theorems. So what's the plan? As I was telling you, so classical limiting theorem, all these initials. CLT means classical limiting theorem. CCLT is complex. No, sorry, I'm messing it up. CLT is central limiting theorem. CCLT is complex central limiting theorem. PLT is Poisson. CPLT is compound Poisson. And then, so the idea will be to reach to a bijection somehow between classical and free things, and that's the Berkovich-Pata bijection, which can define in several ways. Actually, the best way in understanding it is with cumulants. We'll talk about that in the end. So let's have it started. First of all, we have this thing that we already seen last time. So, or even in the first lecture, that's the classical CLT. So if you take self-adjoint variables, which are ID center, same variance T, then these averages, which are not exactly averages, it's averages, but we scale by square root of n, follow in the n goes to infinity limit, the normal law of parameter T. So to prove this, you apply Fourier transform on both sides. On the right side, it's well known. It's exponential of minus t xi squared over 2, xi being the variable of Fourier. On the left side, well, we use the fact that log f linearizes the convolution. So where f, if you want, f of a convolution is the product of the transforms. So basically you have to take, so these variables are ID, so they all have the, let's call x the variable having this distribution. So you have to sum, which in terms of Fourier means to put the n's power, but now you have this factor here, 1 over square root of n, which comes into Fourier like this. So that's the problem, you have to compute this thing when n goes to infinity. And well, this depends only on the moments, right? And so it's going to be something like this, a series. So I mean, the first moment is zeroth moment is 0. Then you get something like this coming from the variance, the second moment, and then smaller terms, because if we don't care about these terms, if we raise to the power n, we're only interested in these two guys. And so we can ignore this, and it goes to this exponential. It's the Fourier transform of GT. We're done. Now, in the free case, exactly the same statement. So the slides, let me do it quickly. So just take a look at the theorem here. Nothing changed almost. So there is an F here, free independently distributed instead of ID. And what changes here is the output measure. We get a linear semicircle law of parameter T. Exactly the same proof, so we compute their transform. And here, once again, their transform is really linearizes. So n gets here. It's an analog of log Fourier, not of Fourier itself. So the sum, the n from the sum gets here. Then this factor here gets like this into the R transform of the computations. Once again, we can ignore the higher terms. So finally get t xi. That's the R transform of gamma t. So gamma t is just the semicircle on minus 2, 2, rescale by t. Very good. Now all this, yeah, let's also see an application of all this. I mean, the classical CLT, of course, we know it applies everywhere because the Gaussian law appears everywhere. Now the free CLT has this this philosophy of probability. This is very nice application to the Wigner matrices. So let's consider Wigner random matrices, meaning ID complex normal entries up to the constraint that the matrix is self-adjoint. So this means if you want to construct a self-adjoint matrix somehow with things as independent as possible, you compute the upper triangular part, you complete the upper triangular part with the ID normal things, and then you reflect, right? And on the diagonal, of course, these guys must be real. So if you want the strictly upper triangular part is arbitrary ID. On the diagonal, you put real guys, also ID. The lower triangular part is the reflection of the upper triangular part. Reflection by changing signs. It's a star operation there. And so these are the Wigner matrices. Now, Wigner's theorem is that each MI follows a semicircle law, gamma t, depending on the variance of the entries. And Voiculescu's theorem now says that these matrices become free, also asymptotically, when it goes to infinity. So this is very beautiful. I mean, these two results are actually Voiculescu's theorem came a long time after the Wigner theorem, and clearly these things go together. I mean, that's the theorem of Wigner matrices. One due to Wigner, two to do Voiculescu. Now there are many proofs. Well, the simplest is by moment method, you just compute, and the moments are the Catalan numbers, which are the moments of the semicircle law. That's for Wigner. For 2 free inertia, you can also get it via the moment methods. There are also some more clever proofs. So yeah, let's just say that it works with the moments. So this was CLT and free CLT. Now let's get to the complex case. So our variables now are no longer self-adjoint. So in a classical case, we can take them to have real and imaginary part, which are ID center same variance. Then the same averages go to the complex Gaussian law, right? Where the proof is just taking real and imaginary parts and apply CLT. So this Gaussian law, I remind you, that's the law of A plus IB, but normalized by square root of t, because square root of 2, right? It's okay. You have a square in there, and that's the diagonal. You have to normalize by a square root of 2. They being independent, each of them following GT. So that's you don't have to reprove this, right? It just follows from the usual CLT by taking real imaginary parts. In the free case, same thing, and you get the so-called Voiculescu circular law. So that's A plus AB. Once again, rescaled by square root of 2, and they being now free, each of them following a semicircle. Once again, we don't have to prove this. That's the usual free CLT. You take real and imaginary parts. But well, these things are tricky. I mean, the complex Gaussian law, the probability, you know that it has many interesting properties that the real Gaussian law doesn't have them necessarily. So if you get into advanced stuff, this limiting measure is very interesting. It's the same case in the free situation. So the circular law has many interesting properties, but which are more technical. We'll be back to this in a few minutes. But for the moment, yeah, from the abstract point of view, that's the result. No need to develop anything new. And finally, yeah, once we have this pair of results, let's talk also about random matrices. That's our policy applications of all this. So we'll take matrices exactly a la Wigner, but no longer self-adjoint. It's just ID normal entries free somehow. I mean, not free, ID, but no constraints. So each of them follows a circular law, and they become free when it goes to infinity. And this, well, the thing is that one doesn't really follow from Wigner. I mean, you need both Wigner and Voiculescu. in order to prove this, because yeah, that's it. I mean, this law gamma t, you see the circular law, you really need freeness here between real and imaginary parts. But the real and imaginary part will be Wigner matrices, so you need that freeness result for Wigner matrices. Okay, so there's a subtlety here. That's why I was telling you that Wigner and Y plus come together. It is really the two sides of the same result, because when wanting to extend it to this setting complex, you really need both things for proving this item 1 here. Now item 2, yeah, that's not very complicated. It's exactly from Wigner plus Voiculescu. Okay, so conclusion we have so far how many 2 plus 2 limiting theorems, application to random matrices, and we yeah, these things come together. Wigner and Voiculescu, they really needed together. Okay, now let's go to the discrete case. So Poisson limiting theorems. Well, in the classical case, that was the result, right? That's the Poisson limit. How's the proof? Let's take a look at that before getting into the free case. So if I take the measure here, so let's go back to the previous slide. So I'm taking this measure and convolution powers of it. So I have to compute the Fourier of this, right? Afterwards, it's going to be easy. So the Fourier transform is given by this on Dirac masses. So for this measure, I get this guy. I have to raise this measure to the power n convolution. So at the level of Fourier, you get a usual power n. And you can write it like this. So, so this guy here is exactly this guy here. And now is the fact that exponential of something is 1 plus something to the n over n power n in the limit. So I get exactly, this means that this limit goes to the exponential of what's here. But that's the Fourier transform of the Poisson of t. So we're done. You see, we prove that Fourier of this goes to Fourier of this. Now, in the free case, well, same method. I mean, you just do the same thing, but with the R transform. And so it's exactly the same measure as before, but now you take the free convolution. And the result is that we get the Marchenko-Pastur law of parameter t, which is this thing here, which is also called, so this was discovered long ago by Marchenko-Pastur in relation with random matrices, with Wishart matrices to be precise. Now, well, since it's also a free Poisson law, so in the literature it's called either Marchenko-Pastur or free Poisson, and it's actually also the square of the semicircle laws. It's three things at the same time. So let's take a look at the proof now. The computations are similar, but a bit more complicated here in the free case for very mysterious reasons. So we start with Cauchy, and then the transform of this. So the R transform out of Cauchy, you get the R transform, right, by inverting and subtracting xi minus 1 factor there. Now, since we are interested in convolution powers of this guy, right? But R transform is just n times the R transform of this convolution power is n times the R transform of mu itself. Now, from this Cauchy transform, we get an equation for this guy. So we get an equation for R just by dividing everywhere by n. So that's your equation. Okay. So what I'm doing, in order to pass from here to here. So I say that R, or rather R over n, because R over n is the R transform of mu, right? So R over n plus the variable, which is now y to the minus 1, should be the inverse of Cauchy. So in practice, I take this formula of Cauchy, and whenever I seek psi, I must replace it with R over n plus y minus 1. So that's what I did here for this psi here, and for this psi here, that's what I did too. Okay, so that's the thing. No, so that's the equation satisfied by the R transform of this guy here, and you cannot really compute it, okay, but you can compute it in the limits. So in order to compute in the limit, first we have to do some manipulations on this. So my claim is that this equation can be written in this form, which is a bit simpler. So what to do? You multiply by n divided by y, because, well, if you would put an n up here, of course, all these guys would disappear to look better. Also, if you divide by y, these guys will disappear and this guy will look better. So multiply by n over y, and then one of the factors, maybe the left one, you put it on the right side here, okay? And you get exactly this. So see the left term here is y minus this guy here after multiplication by n over y, and the term here is exactly here, once again after multiplication by. Well, now you can solve this. I mean, when n goes to infinity, r over n can be neglected. So r over n can be neglected. So I just get on the left t plus yr, and on the right t over 1 minus y. So r finally is t over 1 minus y, which is the R transform of this Marchenko-Pastur law. That's something known. So that's how the proof goes. Well, this might look a bit complicated, but we'll see later. I mean, these laws have many interesting properties, and it's actually something simple. So, as usual, application to random matrices now. So the idea is that the complex Hushar matrices, which are by definition, you take a Gaussian matrix, which can actually be rectangular, not necessarily square, and then GG star. So that's a whole kind of random positive guy, right? Following the n goes to infinity limit, this Marchenko-Pastur law. Once again, t depends on the size, the size of G and the variance of the entries. We'll get back to this later. So very nice. So as a summary now, well, we have all these randomatic things, which are applications, but at the level of free theory, which makes correspond classical and free probability. What we have are six main limiting laws, right? We have here the discrete ones, Poisson, free Poisson, and then here the normal law, Wigner semicircle, and the complex normal law, and the Voigt-Plescu circular law. Now, in addition to this, well, we have some. We're interested also in the relations between all these things. So, what are the relations? Well, here, from you have some complexification, right, which is obvious, from GT to capital GT and from gamma T to capital gamma T. That's just the complexification, it's by definition. Now, an interesting thing is that in the, oops, there is a typo here. That's gamma T here. Voigt-Plescu circular law is obtained by convolving a hard unitary law and gamma T. Yeah, there's a typo, there should be Greek letters here. So there's an extra relation here, which is not exactly this complexification, it's something different. It's a polar decomposition. The polar part of a circular variable is hard unitary, and the modulus is this. And well, you can prove it either random matrices or this kind of Fock space type group monoid things. Now, another thing which is interesting is, and here the statement is correct, is no typo. So there is a relation between this and this, between free Poisson and semicircle. That's something that we've seen already in lecture 1, because at T is 1, SU2, the main character of SU2 is semicircular, and the one of SO3 is free Poisson. And we're saying that the argument is that one character is the square of the other. Well, this is true at any T actually, and you can get it with moments or transforms. The idea is that the moments are Catalan in both cases, but for the semicircle, actually the moments are Catalan, but in between Catalans you have zeros, and for the free Poisson you just have the Catalans. Okay, so it's something like this results a kind of SU2 SO3 type thing somehow. Once again, we'll be back to this one doing quantum algebra later. Of course, it's something quantum algebraic thing. And finally, what is of interest from us are the vertical bijections, right? How to pass from Poisson to free Poisson or vice versa, and same for Gaussian, complex Gaussian. And here, if you look back a bit at the formulas, these are given by the fact that log Fourier corresponds to the R transform. So we have here some formulas. Yeah, for Poisson, for instance, it's T over 1 minus Y. And here, log Fourier, it's this. Well, it's something like this. We'll be back to it. Now, well, let's develop some more theory now. So compound Poisson limiting theorem. We generalize this, the Poisson limiting theorem. You see the problem here, we want to extend a bit this discrete part. So here I have a square, and the idea somehow would be to complete here as to have a cube finally. Okay, so I'd like to have a cube somehow with this being the continuous phase, and maybe this and some other things being the discrete phase. And interesting. So that's why we are now trying to develop this compound free Poisson theory. Well, of course, it's our interest, but yeah, from an abstract thing, let's try to build a cube. So given a measure nu on R, which is actually best taking not a mass 1, but mass t, that's our t parameter somehow, the following limit converges, and the measure is called compound Poisson law. And so that's the first part of the theorem. And the second part is that this compound Poisson law is something very explicit, actually. This can serve as an alternative definition for it. So in the discrete case, where mu is really a discrete measure, some Dirac masses with coefficients, this compound, associated compound Poisson law, is just the law of this sum here. So Zi are the points where the Dirac masses live, and alpha I come from the Ti. They are Poisson variable of parameters Ti independent. So it's a bit tricky somehow you invert. So the Zi's come here and the Ti's come here. So yeah, maybe an explanation for this. So the simplest example is mu is T delta 1. So you see, if I put T delta 1, that's exactly the Poisson limit theorem. So let's see, do we really get here Poisson of T if we do this? So saying T delta 1 here, T delta 1. So here, of course, there is no sum. This guy will be 1, and this alpha will be Poisson of T. So here I just have a Poisson of T variable, so this is Poisson of T. Works. Cool. So that's a statement. Now in the free case, well, exactly the same thing. So what changes here is that we put free convolution and pi here instead of p, and say formula as before, but now the variables are free Poisson of Ti and free. It's exactly the same thing as before. Now, how do the proofs go? Well, in a classical case, it's basically the proof of the PLT, right, which appears like this. But now I have to take linear combinations of guys like this. So it's similar, you get some combinations there. And the Fourier transform on both sides is something like this. It's exactly what we had for the PLT, but it's a sum now. In the free case, well, it's really similar. I mean, it's the proof of the free PLT, which was, let's go back to it. It's, yeah, so it's this. But now you have to put sums everywhere, so it just works the same proof, and you get the R transform on both sides, something like this. So these formulas are actually important too. These are somehow part of the theorem here. It's in 3 parts actually. That's a theorem that the limit converges. the second part is that is the law of these variables. This can serve as an alternative definition. And the third part, which is actually, you can call it proof or part of the theorem, is that the Fourier transforms of the compound Poisson laws and the R transform of the compound free Poisson laws are given by this this formula here. Okay, very nice. So let's see some examples of this. We have what can we plug in? So let's see. So far we have T delta 1, right? We obtain the PLT, free PLT. Now, well, we can, instead of delta 1, we can put the uniform measure on the roots of unity, the complex plane. That's one of the simplest example. We obtain the so-called Bessel and free Bessel laws. The terminology comes from the fact that S is to the density is given by a Bessel function, the second kind. So what are the examples? Of course, of S is 1, right? That is delta 1, the measure on the first roots of unity. So it's in the Poisson laws. Now, the most interesting in the case is S is to infinity 2 and S is infinity. Why? Because S is 2 is the only real case there which can appear besides S is 1. It's a Bernoulli there at 1 and minus 1 is measured on the roots of unity. So that's these are called the real Bessel laws, are denoted just by BT and beta T. And then we're also interested in the case S is infinity. That's the biggest somehow complex case. And here we'll use capital B and well, this Gothic letter, because here we would need a capital Greek letter and there is none. So we use Gothic instead. So this will be the complex Bessel laws. So, well, the good news that is that we have our cube now. So for getting Poisson, which is a bit special, so instead of Poisson, remember we're having this diagram. Let's go back. Yeah. So I have this thing which is very nice here, right? It's continuous laws, so classical free, real complex. Now this discrete side here will just replace this Poisson free Poisson by these Bessel things, real and complex. So you get a cube now. This is very interesting. So you see you have this continuous phase, discrete phase, classical phase, free phase. What else do we have? Real phase here, complex phase below. And the vertical arrows are given by this kind of coefficients of Fourier, must be the coefficients of the R transform. Now the point is that, yeah, this cube are really, is it really good to forget about Poisson? It's a very strange phenomenon there. So on one hand, the free Poisson law is something the most important, but you have to forget it in order to develop this theory, which is three-dimensional. So one dimension is liberation, classical free, the other is real complex, and the other is discrete continuous. So it's very beautiful, but unfortunately, you have to forget about Poisson and all this. Now, well, why not? But what we should do, for instance, the only applications we had is with random matrices. So we should see, are there any random matrices corresponding to these Bessel laws? And the answer is yes, but it's a bit technical, so we'll talk about it later in a specialized lecture on random matrices. So the idea is that if you take a Wishart matrix and you do block multiplications, or other also product manipulations, there's a whole thing here going on, you can obtain this kind of compound Poisson laws, in particular the free Bessel ones. So this is quite technical, but it's actually very beautiful. I mean, if you allow yourself to get beyond Poisson and March-Pasteur's theorem, to get into some of the modern mathematics on the subject, this is it. And these Bessel laws are some of the most important at that level. So finally, this cube, if you're a bit advanced and you're trying to do very modern mathematics like 21st century now, it's very natural you can forget a bit more Poisson. Well, That's it. Philosophical. I mean, it's a bit of a pity that we don't have Poisson here, but the problem is that there's no, if you want a complex analog of Poisson, right? If you want the Poisson law to fit into this law, the problem is that in the continuous case, you have complexification, okay? And the complexification of Poisson would be naturally this complex free Bessel thing. But the real version of the free Bessel thing is the real Bessel thing, is not Poisson. So you see, then that's somehow the phenomena. Okay, well, we'll talk about this a bit more. That's a lot of quantum algebra behind all this. But anyway, so yeah, just to tell you that both from quantum algebra and from the random matrix point of view, it's quite natural to do all this. Now let's try to understand what's the vertical bijection between these measures. So that's basically, well, there's a subtlety here discovered by Berkovich-Pata. So they looked at this problem from a very analytic point of view, and there you have to take semigroups of measures, not exactly measures. And so you take a classical convolution semigroup, a free convolution one, and they're in, you say they're in bijection if the linearization transforms coincide. So once again, convolution semigroups, that's very important from various analytic reasons, and also from the fact that if we go back here, all these are convolution semigroups. We have to put it in the statements. So yeah, main examples. So now I have our cube, and we really have these arrows here, which are the Berkovich-Pata bijection. With the remark about these forgotten things, Poisson, and everything, that actually this Berkovich-Pata works between these Bessel laws and the free Bessel laws for NES. So it covers also Poisson. If you allow yourself to get out a bit of this three-dimensional setting, with arbitrary S, and in particular S is one covering Poisson, free Poisson, that's also covered by all this. No, well, the thing is that actually the Berkovich-Pata bijection is best understood cumulants. That's it's much better than transforms. So what's the idea with cumulants? We'll given a random variable, we'll write log f as a series, and the coefficients are called cumulants, classical cumulants. And same for Dart transform, the coefficients are called free cumulants. And with this, the Berkovich-Pata bijection, even without semigroups, I mean, just tells you that the classical cumulants of the classical measure should be the free cumulants of the free measure. So that is very beautiful, and so that's Schweiker stuff. All before was basically Voiculescu, plus of course these random matrix guys like Wigner and Marcelo Pastur. So that's after all these papers by Voiculescu, this was the main theoretical contribution afterwards, early 90s by Roland Schweiker, this kind of things. Cumulants. So now let's, because this is a very interesting notion, let's go back a bit and go into it a bit. Let's try to understand how this works. The main thing, I'm talking about cumulants. So these were discovered by Rota long ago in a classical case. In the free case is Schweiker. And the main tool there is the moment cumulant formula. So let's explain that a bit. We'll need that later. So the first thing is that you need to extend these cumulants to cumulants depending on partitions. So these are numeric quantities. These are the coefficients of log f and of r. And for some technical reasons, we need to extend them with respect to all the partitions. So instead of this n integer here, we need a pi, which is a partition. And how to do it? Well, your partition has some blocks. So in each block has a certain length, n. And there you put your number, kn of a. So I have kn1 here, kn2 here, kn3 here. You just multiply them. And you declare that this kn here, if you want, corresponds to the one block partitions having n legs. And in general, these cumulants are defined by multiplicativity over the blocks. And with this, you can formulate this moment cumulant formulas, which tell you that the moments are just obtained by summing the components. The subtlety that in a classical case, you need partitions, all the partitions. In the free case, all the non-crossing partitions. So how to prove this? Well, it's basically the Mobius inversion formula. I mean, somehow out of, yeah, you need to invert this thing here. So it comes from the Mobius inversion formula. Not very complicated. Of course, in the free case, there are some problems with the, well, this must be colored integers, right? The moments are indexed by colored integers. Also in the classical case, when it's not self-adjoint, so the technical problems are there somehow with the A, and they start, and I can solve them. So that was about cumulants. Now, finally, let's talk also a bit about moments. So that's something that we forgot to talk, and it's related to this moment-cumulant formula, of course. So we had these 8 limiting laws. Let's go back to them. So the Gaussian laws, Wigner, and all these Bessel guys. So the cumulants, of course, are something very simple because we computed the R transforms and Fourier transforms for everything, including for these Bessel guys. I mean, where was it? In the proof here, you see, that's the proof for the compound Poisson theorem. So the formulas are very simple here. You just have to plug in the measure formed by the roots of unity. The transforms are very simple of the Bessel laws. So you definitely have the cumulants and so the moments. And regarding the moments now, we already talked about this when talking about the Poisson law. I told you that these are the for the Poisson, you get the Bell numbers when t is 1. And also when t is 1, for the normal law, you get this double factorial, which count pairings. Now, more generally, when you pass from t is 1 to t arbitrary, each partition will not contribute with a contribution of 1, but rather with t to the number of blocks. That was the discovery in the classical case regarding Poisson and normal law. So if you want, that's the formula that we discovered long ago. And my claim now is that this works for actually for all 8 laws. With D, I mean the partitions, the categories of all partitions that we're using here being as follows. So let's see. Here we have, where was it? Oops, unfortunately we don't have Poissons, so we have to replace it by these Bessel things, unfortunately. So the static example is here, it's P2. Here in this corner of the cube, we had the normal law. So we agree on this P2, that's something that we proved. Well, this calligraphic P2, calligraphic means matching. I mean, white has to connect with black somehow, or white, black on the vertical. So that's something that you can agree to. Now here we get, for Wigner and Wojciechowski, we get non-crossing partitions. There are many ways of proving this, for instance, with this moment formula. For these Bessel guys, well here at S is 1, let's take this parameter S is 1 to up to infinity. S is 1, we have Poisson, and here we're saying that the moments are the Bell numbers, so you have to put P here. Now, well, in general, when S is bigger, you get the partitions in P such that the size is somehow multiple of S, but the size must be counted with signs because you have black and white things there corresponding to this coming from these colored integers. So you get that this is 2 partitions with even blocks and non-crossing here. And here matching partitions with even blocks and matching non-crossing. So as you can see, there's a lot of algebra here, and what's very interesting with this diagram, so these are no longer moments, but rather the combinatorial things behind the moments. You see, you have all these arrows. I mean, you have inclusions here between these categories. These are plain inclusions. And also you can prove that you have somehow, for instance, if you take the thing generated by this and this is this, I mean, there's a lot of structure here, this 3D structure in this cube, somehow better than in free probability. So that's really quantum algebra. I'll talk about it next time. Now, finally, some further results. We already have many results, but let me tell you, there is not everything is Berkovich path. Actually, there is also the Meissner bijection between. If you take group duals and random walks on them, if you take abelian groups, the simplest one is and you get Meissner, and for free groups you get free Meissner. So this bijection is not exactly Berkovich path. So then there are some unification questions going on. Very interesting things. And finally, there's the last funny thing, which is a very interesting. It's a discovery by was that Belinsky, Leonard Speicher, and Bojejko, Marek. So the normal law is infinitely divisible with respect to the usual convolution. So this means that according to Berkovich path, you have a classical analog. Okay, it's really was the classical analog of the normal law. Sounds a bit bizarre, but makes sense. So, so these guys who discovered it, they have some formula, but it's not very explicit. So it's still, I think, a bit of an open problem. So yeah, many interesting questions. I mean, the basic idea, we have this cube, but with the main objects. But this cube here doesn't contain Poisson. I mean, it's Poisson is something a bit special. And then you have all these other things going around. So the summary now, we have seen definitely, this was the question we were asking ourselves last time, are these really twin sisters? And they are classical probability. Evidence coming from limiting theorems, this Berkovich path bijection. If you want to get beyond this, we have all these quantum algebra problems and the cube, all that really sounds like quantum algebra. And on the other hand, we have these random matrix things which are popping out all the time. So once again, we have to understand that. So, well, we have 2 lectures left. So first one will be quantum algebra, and the one after will be random matrices, the last one.